but rather using arrays. We structured or organized quicksort into a main algorithm and a partition algorithm. I hope you have tried to implement partition algorithm and main quicksort algorithm in the last lab session. The partition algorithm is given an array as the input. It can select any one of the items in the array as a pivot. For example, it may select the last item in the array or the first item in the array as the pivot. The output is, the result is, the array has been partitioned into two subarrays. A left subarray which is less than or equal to the pivot, and a right subarray which is larger than the pivot. For example, 1864039 is the input array. The output array has been, it is the array partitioned into two subarrays. 1403 is the left subarray, less than or equal to the pivot 5, and the right subarray 698, which is larger than the pivot. The partition algorithm achieves this by sweeping the items of the array, by scanning the items of the array once. It reads item 1, item 2, item 3, item 4, 5, 6, 7, 8. So in one sweep of the items of the array, it accomplishes the partitioning. Therefore, the running time of partition is n. To be very precise, partition algorithm makes n minus 1 comparisons. It hardly takes 5 to 10 lines of code to implement partition. But in the last lab session, I would have asked you to do it in maybe 4 steps or 4 parts. The intention of the 4 parts is to force ourselves to think about various steps of the algorithm. An algorithm or a code that implements the algorithm is not taken out of ready-made showcase. If all the time we are taking an algorithm or its code out of a ready-made showcase, we will never train ourselves to think rigorously about how to start constructing an algorithm, how to develop the construction of the algorithm step by step, and how to bring the construction to completion. We would never have trained ourselves in the construction of algorithms or code. So that was the purpose of breaking such a small, simple, straightforward algorithm into a number of parts. This is the algorithm. I'll come to this in a moment. Once we have partition, the main quicksort algorithm itself is quite simple. It is a recursive algorithm, tree recursion. That means one call to quicksort makes 2 recursive calls, line number 3 and line number 4. In a recursive algorithm, we have to ensure that the input size to a recursive call is strictly smaller than the input size to the original call. The input size to the original call is from low to high. Here the input size to the recursive call is pivot minus 1. Similarly, pivot plus high. The subarray passed to the first recursive call quicksort will be at least 1 less than the subarray here. Similarly here, That is because we have removed pivot element out of consideration. So these are the recursion step, and the base case is if the input is an empty array, the output is also an empty array. If the input is a singleton subarray, the output is also a singleton subarray. Okay. Now for the analysis of the running time. Oh, this is trace. You should know how to trace the working of an algorithm on an example. Example 186403995. 5 is selected as the pivot. Left subarray is 1, 4, 0, 3. Right subarray is 8, 6, and 9. Okay. The order doesn't really matter. 6, 9, 8. Then in 1403, 3 is selected as the pivot. 1 and 0 are the left subarray, 4 is the right subarray. Whatever I have shown in blue, I have shown the pivots in blue. Pivots, a pivot has come to its final position in the sorted array. Once a pivot has been selected and come to the final position, its position will not change anymore. So 5 will be in the same position thereafter. So 3 will be in the same position. Okay, between 1 and 0, 0 is the pivot. It is in color blue. It has come to its final position. Left subarray is empty. Right subarray is 1. Okay, in this subarray, 1 is the all right. Then since it's a singleton list, input is 1, output is 1. And then we come to 4. 4 is a singleton list, therefore the output is 4, and so on. Okay, now we come to the main discussion for the day. We want to analyze the running time of quicksort. It selects a pivot arbitrarily. Our desire is whenever we are given a subarray from low to high, the pivot should be so selected that the smaller subarray less than or equal to the pivot and the larger subarray greater than the pivot should be roughly equal in size. That is our desire. When will that be achieved? When will the two subarrays be roughly equal in size? For what choice of pivot? Can anyone answer this question? Right now, we said the pivot will be selected arbitrarily by the algorithm. How should the pivot be selected? Or if we select the pivot in this way, that will ensure the left subarray less than or equal to and the right subarray greater than will be roughly equal in size. For what condition of pivot this will be true? Can anyone try to answer this question? The median of the steps. Exactly. Given an array low to high, if we are fortunate enough to choose the median of the subarray low to high, You will recall that median in a set of numbers has this property. There are equal number of items below the median and above the median, and that is what we desire. But I said the algorithm selects the pivot arbitrarily, or it always selects the uh, item at low as the pivot, or maybe it always selects the item at high as the pivot. We never said the algorithm takes care to select the median element as the pivot. Okay. So it is our desire, if the algorithm is so designed to select median or approximately the median, then the array will be divided into two subarrays of roughly the same size. Then we expect to achieve the benefit of divide and conquer algorithms. Suppose in the worst case, the array is already sorted. Let's say 2, 4, 5, 7, 9. And we always select the first element as the pivot. What will happen? 2 is the pivot, left subarray will be empty, right subarray will be 4, 5, 7, 9. Then 4 will be selected as the pivot, left will be empty, right will be 5, 7, 9. 5 is selected as the pivot, left will be empty, right will be 7, 9. 7 is selected as the pivot, left will be empty, right will be 9. This is the extreme case. In general, if there are n items in the array and the array is sorted, left subarray is 0, right subarray is n minus 1, of course there is one pivot. Then the next recursive call, left subarray is empty, right subarray is n minus 1, n minus 2, and there is one pivot. And next time 0, n minus 3, and 1, and so on. So if there are n items, how many levels will there be in this recursion tree? If there are 5 items, 1, 2, 3, 4, 5 levels. If there are n items, there will be n levels. You say the depth of the recursion tree is n, or n plus 1 or n minus 1, whatever it is. This is the worst case. The worst case of quicksort occurs when the input array is already sorted. Take a note of this point. If the input array is already sorted, it is not a help render to the quicksort. When the input array is already sorted, it is then the worst performance is given by quicksort. What is the performance anyway? Okay, we said n is the input size to the call. It divides it into 0 and n minus 1. Let me say t of 0 is equal to 0. The running time of a subarray of size 0 is 0. The running time of quicksort and a subarray of n minus 1 is t of n minus 1. Quicksort itself does n minus 1 comparison. We are measuring the running time in terms of the number of comparisons. Effectively, we are asking how many comparisons does a call to quicksort make if the input array has n items? We are saying how many comparisons are needed if the array has n minus 1 items, plus the main quicksort algorithm itself does n minus 1 comparisons by calling partition. Every contractor must do at least some work before he gives some subcontract to others. Partition makes n minus 1 comparisons. Therefore, if we expand, it will be n minus 1 plus n minus 2 plus n minus 3 and so on plus 1. This is equal to n minus 1 times n over 2, which is n square minus 2 minus n by 2. This is, okay. If I discard the lower order terms and the constant coefficient, it is n squared. Therefore, we say it is big O of n squared. Remember, the running time of insertion sort, the running time of selection sort are also the same, big O of n squared. Therefore, the worst case running time of quick sort is no better than insertion sort or selection sort. We were expecting for something glorious, but nothing like that happens. This is an important question. When does the worst case occurs for a quick sort? This is somewhat similar to insertion of items in the binary search tree. The intention of organizing items in a binary search tree is to improve the search time. The search time will be the best if the height of the BST is small. It is a short, we want short, bushy BSTs. Suppose we are inserting a list of items which are already sorted, something like 2, 4, 5, 7, 8. What will be the shape of the binary search tree? Or what is the height of the binary search tree? If the items arrive at this order, first 2, then 4, then 5, then 7, then 8, then 9, then 10, and so on, what will be the height of the binary search tree? Can anyone respond?
N, sir.
What?
Equal to the number of elements, like 2, 4, 5, 7, 8 will be a skewed right tree, sir.
Yeah, it's basically it will be 2, 4, 5, 7, 8, 9, 10. So it is not at all a tree, it is just a list.
Yes, sir.
We dreamt for a tree but got a list. A similar situation here. Let us go on. When does the best case happens? We have already argued. When the best case happens, when the pivot is selected, the pivot selected is the median of the array. Then given the input array is divided into two subarrays of roughly equal size n by 2. Therefore, the running time T of n of quicksort algorithm is, what is the running time for an input size of n by 2? T of n by 2 comparisons. Since two recursive calls are made, it is 2 times T of n by 2. And the main call itself makes n minus 1 comparison. And therefore, we have solved such divide and conquer recursions. It is n log n. We know that big O of n log n is far better than big O of n squared. Big O of n log n grows more slowly or as fast as big O of n squared. This is great. But the best case occurs very rarely. How do we know that the pivot that we have selected is the median of the array? Therefore, we want to analyze the average case running time of quicksort. In the whole course, we do not analyze the average case for many different algorithms. But for quicksort, in the average case analysis we do, I quickly run through it. Okay. This is the given array, let's say 0 to n or 1 to n, whatever it may be. The partition makes n minus 1 comparisons. It scans the array once from 1 to n, making n minus 1 comparisons. The pivot is equally likely to come into position 1 or position 2 or position 3 and so on. If the pivot falls into index 1, left subarray size is 0, right subarray size is n minus 1. If the index falls in position 2, left subarray is 1, right subarray is n minus 2. If the index falls if the pivot falls in index 2, left subarray is 2, right subarray is n minus 3. Note that the total will be n minus 1, n minus 1, n minus 1 because we have removed the pivot itself and so on. If the pivot falls into n minus 1, then the left subarray will have n minus 2 elements and the right subarray will have 1. If the index falls right on the last index, it will be n minus 1 and the right subarray will be 0. Now all these cases are equally possible. Pivot in 1, 2, 3, n minus 1, n. The probability that pivot is in index 1 is equal to the probability that the pivot is in index 2 is equal to the probability that the pivot falls in or comes to index 3 and so on is equal to the probability. What is the probability? 1 by n. Probability that the pivot falls in index I is equal to 1 by n. So what is the running time here? T of 0 plus T of n minus 1. How about here? T of 1 plus T of n minus 2. How about here? T of 2 plus T of n minus 3 and so on. This is T of n minus 2 plus T of 1, T of n minus 1 plus T of 0. And this has a probability 1 by n, probability 1 by n, probability 1 by n, probability 1 by n, probability 1 by n. This 1 by n is common, we can take that out and you can add all these things together. And you can easily observe T0, T1, T2 and so on, Tn minus 1. Here we have T0, T1, T and so on, Tn minus 1. So this T0 plus T1 plus T2 plus T of n minus 2 plus T of n minus 1 is double. Therefore, this is what we get. What is the expected or mean running time T of n? Okay. Expected running time of or expected value of T of I minus 1 plus T of n minus I. Basically, this is what we have done. 1 by n, T of 0 plus T of n minus 1 plus 1 by n, T of 1 plus T of n minus 2 and so on. So this is T of 0 plus T of 1 plus T of 2 all the way to T of n minus 1. Since each has the probability 1 by n, multiply that by 1 by n and there are two terms that we have doubled. So this is the expected or average running time. T of n is equal to sum of T of I for I is equal to 0 to n minus 1 multiplied by 2 of n. This is called a full recursion, full history recursion. Recurrence. On the left side you have T of n, on the right side you have T of n minus 1, T of n minus 2, T of n minus 3 all the way to T of 0. The entire history of recurrence occurs here. This is a little hard to solve. We will try to solve it. This plus the call itself does an amount of work equal to n minus 1. The quicksort algorithm, this is due to the recursive calls, the average number of comparisons or average time due to recursive calls. This is the number of comparisons done by the call itself. Therefore, we have this. T of n is the average running time. Okay. Put up with me for some algebraic manipulation, but we have to live with this evil for some time. Do it carefully. Okay. Multiply throughout by n. Therefore, this n will cancel out. This is n times n minus 1 and this is n times. That's what I have written here. We want a normal recursion, a first order recursion. A first order recursion is something like this. T of n should contain only T of n minus 1. This is called first order recursion. If T of 1 is expressed in terms of T of n minus 1 and T of n minus 2, that is a second order recurrence. But what we have right now is a full history recurrence. We want to, from the full history recurrence, we want to derive a first order recurrence so that we can solve. That is our goal. If this is the recurrence for T of n, what can we say about T of n minus 1? Replace every occurrence of n by n minus 1. Replace 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 n by n minus 1. You get n minus 1 minus 1, therefore n minus 2. Here, replace n by n minus 1, you get n minus 2. So this is for T of n. This is for T of n minus 1. Our goal is to get a first order recurrence. Therefore, from here to here, subtract n times T of n minus n minus 1 T of n minus 1. Here, n minus 1 is common. So anyway, n times n minus 1 minus n minus 1 times n minus 2. How about here? Just to make things a little clear, I have expanded it. T of 0, T of 1, T of 2, and so on up to T of n minus 1. This term. And I have expanded this also. T of 0, T of 1, and all the way up to T of n minus 2. When we are subtracting, this will go, this will go, this will go, and we will be left only with T of n minus 1. That's it. Plus T of 2 times n minus 1. Here, n minus 1, if you simplify, n minus n plus 2, therefore n, right? Okay. All right. This is n minus 1 minus n plus 2, n cancel. This is plus 1. Oh, no, this is not there. N minus n minus 2, therefore 2. So 2 times n minus 1. We want to express T of n alone. Therefore, bring this n minus 1 T times n minus 1 on the right side. We get n times T of n. Simplify this stuff. T of n minus 1 has 2 and n minus 1 is the coefficient. 2 plus n minus 1 will be n plus 1. Divide the whole thing now by n times n minus 1. So this n will go and you will get n plus 1. This will be n times n plus 1. This n plus 1 will go n. Okay. This is more or less what we want. Just one slide away. We have got rid of the full history recurrence. Now we have the first order recurrence. T of n is expressed in terms of T of n minus 1, but not that simple kind of first order recurrence. T of n has a coefficient 1 by n plus 1. T of n minus 1 has a coefficient 1 by n. A little difficult. All right. If we unroll, what will happen? The right side. T of n by n plus 1, I am just copying from this page. T of n minus 1 by n plus 2 times n minus 1 by n plus 1. So this term you will write for 2 n minus 1 n plus 1. Then after one expansion, it will be 2 n minus 1 by n minus 1 plus 1. After one more expansion, this will be 2 n minus 2 minus 1. This is n minus 2 plus 1 and so on. Basically, Instead of 2 times n minus 1 by n plus 1, let me write 2 times I minus 1 by I plus 1. This term has to be evaluated for first n, then n minus 1, then n minus 2, and all the way to 2, 1. That's what I have written here. If we unroll the right side, we will get t of 0. Okay, n is equal to 1. When n is equal to 1, t of 1 minus 1 will be t of 0 divided by 1. And here, I is equal to 1 to n, sum over 2 times I minus 1 by I plus 1. T of 0 is equal to 0, let's assume. So this is what we get. Let us simplify this. 2 times I minus 1 by I plus 1. Expand that. 2i over I times I plus 1 minus 2 over I times I plus 1. If we remove this term, this will be the whole thing will be less than 2i plus 1. Something like this. I minus 2 is less than 5. Something like that. Okay. I and I get cancelled. You get 2 over I plus 1. If we drop I, drop this plus 1, this is going to be less than 2 by I. These are simple algebraic manipulations. And therefore, I will write this as less than sum of I is equal to 1 to n 2 by I. Let me copy it in the next slide. Here. T of n over n plus 1 is this. A little bit of knowledge from integral calculus. Sum of 1 by I for I is equal to 1 to n is almost equal to integration of 1 by I di for the limit from 2 to n. If you are summing from I is equal to 1, the limit has to be I is equal to 2. You have seen that. You know that. It is a curve and you approximate that by sums. The sum of little squares, little rectangles will be definitely less than or equal to this. 1 by x dx is log x. Therefore, this is log I. Apply the limits from 2 to n. Log n minus log 2. This is less than log n. So now I will say this is less than 2 log n. And that's what I have written here. T of n over n plus 1 is less than or equal to 2 times log of n. Simplify. T of n is less than or equal to 2 times n plus 1 log of n. Okay, this term is not needed. This is 2n log of n plus 2 times log n. If you compare these two terms, log n is very small. This is lower order terms. And drop this constant and you get big O of n log n. Fortunately, the average running time of quicksort is big O of n log n. Okay, this you have to go through the derivation carefully. That's all. The work for the day is over. We have a little bit more time. What I'm going to do is, we have already done merge sort. Let me just summarize those stuff. This is not a new topic. When we discussed about divide and conquer recurrences, we use merge sort as an example. Therefore, I don't need to do this stuff. I'm only repeating. Suppose you're getting 832975154. You split it into roughly equal sized halves. 83297154. Then split it into roughly two halves. 83 and 29. Split it into two halves. 8 and 3. Then merge them. It will be 3, 8. And then here 2, 9. Split it into two halves. Merge them, it will be 2, 9. Then merge 38 and 29. 38 is sorted, 29 is sorted. When you merge, it will be 2, 3, 8, 9. Now come to the other half, right half. Split it into two halves, 7, 1, 5, 4. 7, 1 and 5, 4. Split it into two halves, 7 and 1. This is sorted, this is sorted. When you merge, it will be 1, 7. Split this into two halves. 5 is sorted, 4 is sorted. When you merge, it is 4, 5. So 1, 7 is sorted, 4, 5 is sorted. When you merge, it is 1, 4, 5, 7. 2, 3, 8, 9 is sorted, 1, 4, 5, 7 is sorted. When you merge, it will be 1, 2, 3, 4, 5, 7, 9. 7, 8, 9. That's how merge works. Okay. Just as we organized, okay, let me ask a question here. We want to compare the two sorting algorithms quickly. Quick sort, this is how I write. I don't leave space between quick and sort. Similarly, I don't leave space between merge and sort. Merge sort, a single word. Quick sort, a single word. Let us briefly compare very quickly. Given a instance, both algorithms break them into sub-instances. Then you have sub-solution, a sub-solution, then both into a solution. So this is the divide part. Divide the instance into two sub-instances. We have sub-solution for one sub-instance, sub-solution for the second sub-instance. Then you combine the two sub-solutions into a solution. Okay. Listen to me carefully and answer. Whenever a call is made, some amount of work is done by the call itself, the algorithm itself. The remaining amount of work is done by the recursive calls. Quicksort does some amount of work in dividing, some amount of work in combining. Mergesort also does some amount of work in dividing and some work in combining. You have to compare. Now we have seen mergesort. If it is an array, to divide an array into subarrays, what is the amount of work? You have to say in terms of 1 or n or log n or n log n. Constant work or linear work and so on. To divide the input array into two subarrays, what is the amount of work or what is the running time taken by mergesort? What was the running time taken by quicksort? The input was an array. Then how does it divide the array into two subarrays? A smaller than or equal to subarray and a larger than larger subarray. What was the time taken? For quicksort, okay. To divide an array into two subarrays, a less than or equal to pivot subarray and a larger than pivot subarray, what was the time spent?
N, sir.
N. What was the time spent once we have the sorted left subarray and sorted right subarray? Did quicksort need to do any work to combine?
No, sir.
No, it is 0. Therefore, for quicksort, for dividing it does work, the time spent is big O of n. For combining it is 0. Alright? What can you say of merge sort? You are given an array, let's say 1, 2, 2, 3, 4, 5, 6, 7, 8. You have to break that into 1 to 4 and 5 to 8. All that you have to do is calculate the middle index. Once you have calculated the middle index, okay, you say one subinstance is 1 to 4, the other is 5 to 8. Do we need to scan all the elements of the array in order to calculate the middle index?
No, sir.
No. So what is the amount of work done for dividing?
None, sir. Just a single.
0. But when it is given two subarrays, two sorted subarrays, 2, 3, 8, 9, 1, 4, 5, 7, to merge two sorted subarrays into a single sorted subarray, it has to scan all the elements of the two subarrays. It has to scan 2, 3, 8, 9, 1, 4, 5, 7. In fact, 2, 3, 4, 5, 7, 8, 9. What is the amount of work done?
N, sir.
N. Contrast that. Quicksort does work to divide, no work to combine. Mergesort does no work to divide. It does work to combine. It's just a comparison between mergesort and quicksort. Okay. We also organized mergesort as a main algorithm and a helper algorithm for merging two sorted lists. And this is the main algorithm. Find the middle index. Start to M is one subarray, M to end is the another subarray, merge sort one subarray, merge sort the other subarray, then call merge to create a single sorted subarray. This was the basic idea. This is the main algorithm. And this was the helper algorithm merge. This is base case. And this is recursion step. And we are using list, very important. If A is empty, A and B are sorted. If A is empty, output will be B. If B is empty, output will be A. If neither is empty, then we will compare the 0th item of A with the 0th item of B. Pythonic. Okay. Deconstruct A to the head and the tail. Merge tail of A with B, then put A at 0 at the head and so on. Homework, I may not be able to complete it in this class. What I want you to do is this. Instead of implementing the main algorithm merge sort and the helper algorithm merge using list, you have to use an array. Those are two different stuff. This is merge sort using array. You are given a subarray. Low, high. Suppose this is mid. Okay, I am always this point. This is high. The input is low to high. One subarray is low to mid, the other subarray is mid to high. So merge sort subarray A low to mid, merge sort subarray A mid to high, then merge. This is sorted because of line number 3. This is sorted after merge sort line number 4 returns. Two sorted subarrays you have to merge. The base case is you have to check. Low to high subarray has 0 items or 1 item, it is a base case and you have to return. So compare this with this merge sort. There is no need for keeping track of low and high. Here you have to do that. Harder still is merge. This is low, this is high, okay, and this is M. We need an auxiliary array for merging. Low to high. And then you have to maintain 2 indices here. I, J, and this is something like K. L to I and M to J has already been merged and put in L to K. If this is A, this is B. Now we have to decide whether we have to copy A at I in B at K or A at J in B at K. One of the two will come here. Either this or either that. Which one should come here? Remember, this is already sorted. A to L to M is sorted. M to H is also sorted. L to I subarray and M to J subarray have been merged and put in L to K. Try to answer this question. Between I and J, which one should be copied in K? This or this? How will you decide? Can you answer?
Whichever is lesser, like the
Yeah.
value.
If A at I is less than A at J, B at K becomes A at I here. B at K becomes A at I, and I alone should be incremented. Okay, I think the whole thing, yeah. Of course, I should be incremented, K should also be incremented, but incrementing K I'm taking care of with the for loop. If J is smaller, B at K becomes A at J, and J should be incremented. Of course, K should also be incremented, but K incrementing I am handling with for loop. Instead of writing 2 assignment, I write P of K, comma, J, this is J. P of J, P of K, comma J become A at J and J plus 1. So this is the suppose it is possible that I is equal to M. That means all the items of the left subarray L to M have been copied here. So before we compare item I and item J of array A, we should check whether I is already equal to M. If I is equal to M, that means I have exhausted the left subarray L to M. Then all I have to do is without comparison, just copy A at J. This is what I do here. If I is already equal to mid, no need for copying anything. B at K becomes A at J and simply increment J. Similarly, if I have exhausted M to H, how will I check? Check whether J is equal to H. All right, that's the algorithm. How do you compare this merge algorithm with this nice algorithm, which seems better and easier to understand? Using list or using arrays? What is your take?
So using list looks simpler, like
Sure.
Definitely.
Yes,
Even
sir.
in terms of the number of lines of code,
yeah.
hardly, basically 1, 2, 3, 4, just 5 lines of code. Okay. Here, there is so much to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Finally, you have to copy. So, by sheer line count, it is more complex. But that is not the main point for me. I can write 10 lines or 20 lines. I am not troubled by that. You know what troubles me the most? I have to keep track of this I, J, K, O. Am I correctly updating I, J, K? There is no need for these 3 state variables in the list version. All that I have to deal with is the tail and head of a list. That's all. There is no need for 3 state variables such as I, J, K to keep track of how much of each subarrays and the final array I have constructed, I have scanned. The more the number of state variables, the more complex the algorithm is to understand and more prone to bugs. So my reason is not that merge using arrays is longer, takes more number of lines of code. My reason is every state variable introduced into an algorithm is a potential source of a bug. It makes understanding or changing the algorithm all the more difficult. Okay. What is the running time? It is still same, big O of n, because we are scanning all the elements of the left subarray, all the elements of the right subarray. If totally they have n items, we are scanning n items. That's it. Analysis we have already done. There is no need for average case because in merge sort, the 2 sub-instances are always balanced. So if T of n is the number of comparisons for merge sort call, it makes 2 merge sort recursive calls. For each recursive call, the running time is the number of comparisons T of n by 2 plus T of n by 2, and merging takes time n. Therefore, this is T of n is equal to 2 times T of n by 2 plus n. So analysis is straightforward. We have already done it when we studied recurrence relations and we got n log n. Same as quicksort. Quicksort is also running time big O of n log n. Merge sort is also n log n.